want to get like a very casual thoughts on, I mean, what are your challenges that you have seen while probably deploying LLM? Because today's session is more about deployment, right? So I'll not talk about what are the challenges associated with training, but I just want to hear some raw thoughts from you, like when you have tried deploying an LLM, what are some of the most challenging things that you have come across that your organizations are asking that you want to get addressed?
Yes. So first is the scalability. How do we deploy in a scalable and cost-effective manner?
Right.
Right. Even if availability of GPU is there, how do we scale it to say? Let's take the example what in the first presentation we saw. Right. If you have to deploy it to say hundreds of users, how do we scale it? I know there are frameworks like TensorRT-LLM and all of those things, but where are they? Again, availability of chips is another concern. Right.
Right. Okay, so first is availability of chips, infrastructure. Second concern is that, hey, how do I deploy it effectively for 1,000 users and make it cost effective, right? Because everybody wants to make money out of this. I mean, nobody deploys LLM for fun, right? It's about generating money for your organization. So how do I go ahead and actually reduce the cost so that you guys who are building the end application can actually start making money? So 3 key points that I heard: infrastructure, scalable deployment software toolings, and third is reduction of cost. Anything else?
How do you have in single GPU multiple models? For example, in Relive and the database, they have adaptive swapping,
Right.
main memory, and you have SLMs instead of large LLM. So that approach probably is going to reduce the
Cost.
quite drastically. And the approach itself is instead of large language model, SLM probably will be more effective on the starting point.
Sure. Pretty good point. Like, can I actually host multiple models on a single GPU? And will it actually reduce down my cost? Like, again, that's a question. Okay, so anything else?
I don't know, tool specific question, but are you going to cover something related to Triton inference server or those things?
We would, yeah.
Appreciate
Yeah.
that.
I absolutely, that's the whole point. Okay.
There is one more throttling piece, because the throttle limit is not just for tokens, it is per second, and within that also there are complications. So how do you essentially make for huge, high scalable systems in memory cache alongside with some kind of a worker threads which actually can manage the throttling with other API-based calls that you do there.
Right, so basically increasing the throughput and ensuring that the latency is as low as possible,
Yeah.
so that it feels real time. Okay, pretty great question. Anything outside of this? Or okay.
Accuracy.
Okay, pretty good point. Like while deploying, if I'm quantizing how much accuracy am I going to lose, and how do I make sure it's as good as anything that's running on say FP32?
I think some company has introduced like 1 bit.
Yes, it just came out. I think very interesting people. A lot of discussion going on around that also within NVIDIA. But yeah, that's right. It's a very interesting people.
So every organization will have some limited GPU machines, right? But there are different teams who wants to utilize this.
Right.
How can we have like two kind of a concept, like where we can leverage GPU for all the teams and equally portion, something like that?
Again, another very good question. How do I build a system architecture on top of the GPU infrastructure to make sure that multiple teams can use GPUs, right? Because I'm sure getting 1 GPU per person or probably more than 1 GPU per person sometimes gets harder, right? So how do I manage less number of GPUs, but even if I have say like more number of users, how do I sort of manage that kind of a queuing system? Again, very good questions, but I'll try addressing some of these. Some of these questions I'll try addressing after the session because it's not related to deployment per se. But again, very good questions. And okay, so what I really want to show first is that where will LLM end up impacting us? Because at the end of the day, we talk about LLM can do this, LLM can do that, but I want to show you some examples just so that it just opens up everybody's mind of what kind of applications can we go ahead and look into in the future. Okay, weird.
Amijurum Research Edu.
Mizoram Research.
Okay, so this just to give a little background.
Sorry.
Yeah,
Mizoram.
just a little background. So this is basically more like a voice-enabled LLM system that allows you to ask queries around government schemes on a portal. Now, why is this critical and why will it have impact, right? Today, you see that there are thousands of government schemes, but the problem is that nobody, especially people like farmers and other people who are not very comfortable with digital infrastructure on their phone, they cannot go on a website, go find that information somewhere which is hidden somewhere, right? How do you bring that information which is hidden across these websites and make it more accessible just through your voice, right? Is it possible? And that's what we are trying to show in this demo, that hey, instead of you as an end user, right, probably anybody who benefits from government schemes, how can you just simply ask a question through your voice in your own language and get an answer that tries to give you that answer in the most effective way. So let's just look at a quick demo around that.
मिजोरम रिसर्च फेलोशिप क्या है?
मिजोरम रिसर्च फेलोशिप सरकार के उच्च और तकनीकी शिक्षा विभाग द्वारा एक फेलोशिप योजना है मिजोरम का। इस योजना का उद्देश्य उन अनुसंधान कार्यकर्ताओं और शिक्षकों को वित्तीय सहायता प्रदान करना है जिनकी आयु 45 वर्ष से कम है, जिन्होंने अनुसंधान के लिए अपनी प्रतिष्ठा स्थापित की है या डॉक्टरेट की डिग्री प्राप्त की है या अपने श्रेय के लिए अनुसंधान कार्य प्रकाशित किया है और स्वतंत्र अनुसंधान कार्य के साक्ष्य दिखाए हैं। आवेदक को पिछले विश्वविद्यालय की परीक्षा में औसतन कम से कम 50 अंक प्राप्त करने चाहिए। यह योजना मिजोरम के वास्तविक स्थायी निवासियों के लिए खुली है।
प्रधानमंत्री आदर्श ग्रामीण योजना एक लाइन में बताएं।
प्रधानमंत्री आदर्श ग्रामीण योजना (पीएमजीवाई) एक ऐसी योजना है जिसका उद्देश्य प्रासंगिक केंद्र और राज्य सरकार की योजनाओं और अंतराल भरने वाली निधियों के अभिसरण कार्यान्वयन के माध्यम से अनुसूचित जाति बहुल गांवों का एकीकृत विकास करना है।
So I'm just going to shorten the demo because we have slightly less time, but I think it just gives a hint, right, of what is possible and how is it actually going to affect and impact the end users who will start using it, right? At the end of the day, it's just not about building enterprise applications. Sure, that is the case, but how do we build these voice-enabled LLM systems to impact the end users of India, right? Basically the citizens, so that they can actually benefit from a lot of the things that government and other organizations are doing. Now, on a very high level, what does the architecture look like? Because a lot of people ask me this question, and it's pretty simple. So you have an ASR which basically converts your raw voice into the textual format. So whatever query you had asked got transcribed from your speech to the text. Second, we use 4 modules. One is the LLM, obviously to generate the answer, but outside of that, what's important is doing retrieval augmented generation. The reason why this is critical is because you want to make sure that the answers that you're generating, you know where the reference came from for that answer. And that's where RAG or retrieval augmented generation helps. What it basically does is, like, a very simple thought process to think about it is, you go on Google, you type a query, you get thousands of results. Now outside those results, you're going to probably shortlist 3 to 4 of them, which is what the re-ranker will do, and then give you like the top 3 results. You take chunks based on the query that you had asked, so there will be certain chunk of information that will be there. You sort of concatenate those chunks, put the query on top, put the concatenated chunk, provide that as a large prompt, send it to the LLM system to then generate the answer. Now, the best part is that if somebody asks that, hey, from where did this answer get generated from? You can say that, hey, I had retrieved these particular chunks from these documents, or probably even from the web. So there is a very good option of actually going back and referencing where this data was generated from, right? If that makes sense. So once you have that, you want to generate the answer from the LLM in a streaming way. That means you don't want to wait for the entire generation to happen. You want to stream the data which is coming in from the LLM and send it to a TTS system that can further stream the text that was generated from the LLM in real time, so that there's no delay of 5-6 seconds, because if there's a delay, people are not going to end up using it. Okay, before that, let's do for people who are probably slightly new to LLM, I just want to do a very quick brief of how does LLM work from first principles. So what I'll do is I'll go to I'll just show a quick small code base that sort of gives you an idea about what are the different components that go inside LLM inferencing. Again, it's going to be very fundamental, so for people who have been already working on these things might find it quite straightforward, but just for those people who are a bit new, I just want to make sure that everybody's on the same page. So we have imported basically some of these functions from this transformer library, which is from Hugging Face. Now I've loaded the model and something called as a tokenizer. The way to think about a tokenizer is very simple. Computers don't understand strings directly, right? That means these LLM models don't really, or neural networks don't understand text directly. What they really understand is numerical values. So what do is you take the text that has come in from the user, which is basically this particular prompt. You do the tokenization, which is converting that particular string from text to some numerical format, which in this case is going to be integers. Now let's look at it after tokenization. How does it look like? So as you can see, there are 2 keys in this dictionary. One is input IDs and attention mask. Ignore the attention mask for now. The important one is the input IDs. this is basically giving you the tokens that were not generated, but the tokens that were the tokens and their associated index ID within the tokenizer. How does that look like? So if I just take the tokenizer and then I just say tokenizer.vocabulary, you can basically see that every word has some ID associated with it, right? That means what has happened is that this sentence, which is hey, are you conscious, and even the comma, all those got converted to these integer numbers, and there is a mapping between those words and the integer numbers, and that is what the vocabulary is. So what I'm just going to simply do is I'm just going to take the word to ID to mapping, and then I'm basically going to take these numbers that you saw, which is this list of numbers, which is 1,18637, and convert that to the corresponding string, so that you can see that. So yeah, so basically after tokenization, this is the string that you're getting, or the tokens that you're getting. Okay, so this is what this is how the program is looking at the input string that you had. Now you take these numbers, which is these numbers that I showed you early on, which is 1,1863729 and so on and so forth. You're taking these numbers and then you're feeding it to the model that is taking this input, and then you are saying that, hey, how many tokens should you generate? In this case, 30 is the maximum length of tokens that I want to generate. And now you can see that it has generated 30 tokens. Now these IDs need to further get converted back from these numerical formats to a corresponding text, and that's where we're going to use a batch decode function that will simply convert these IDs back to the string, and this is how it will look like. So the question was, hey, are you conscious? Can you talk to me? I'm just an AI, I don't have consciousness. So again, just LLM 101, just so that you just get an end. So you have a pre-processing stage, you have model generation stage, and then you have a post-processing stage. Now let's go back to the slides, and let me give you a little bit of that view from a computational standpoint, like what is happening on top of the GPUs when we looked at those 3 steps, because that's important to understand, and once you understand that, you'll have some idea about how can you optimize it further. Okay, so there are these 2 stages in typical LLM deployments or any LLM inferencing, which is basically a pre-fill stage and a decoding stage. So a pre-fill stage is where you take multiple prompts coming in from users, batch them as a batch of input, and then you basically take that batch and then you send it to the LLM model. Now the LLM model needs to look at these different prompts from different users that have come in, and then there's going to be stage of this pre-fill. This is where you're going to parallelly execute on all the prompts that have come in from the user. Okay, so this is one compute step. Now the next part after this is called as the decoding step. That is where the model is going to start generating the next token, and as soon as the next token is generated, it will take that output token, it's going to take it and feed it back in to the model again, and then it will generate another token, and it will take that, feed that back in, it will generate another token. So you just keep doing this decoding step again and again till the time you have not generated all the possible tokens. So these are the 2 quick stages, and the first phase, which is the pre-fill stage, because you have all the prompts already provided by the user, you can basically leverage GPUs for doing a quick large matrix operation and working on all the prompts directly in one compute cycle. But the problem is when you're doing decoding step, because you cannot finish decoding in one compute cycle, you need multiple iterations, because you're generating something, you're feeding that back in, and then you're again doing the computation on the GPU. So it's like a continuous process that you're doing during the decoding step. Yeah. So let's again take an example. You have an input. The token is write a story about NVIDIA. Send it to an LLM, and then it'll say that hey, and then it'll start generating. So say the first thing. So you have sent this text. This is the state of that particular query. And then you'll start generating one token, like once upon a time in, and you'll probably generate like a very long text, and you'll keep doing that till the time you don't reach an end of sentence token. Once you reach end of sentence token, it will stop generating. Okay, so this is a very very high level view of how the entire computation thing works. Again, not in a lot of details. Now let's go to the second part. How do we look at indic text generation? because all these models that you actually see, which is in open source, are built for English, right? That's why you see that people are using it for English. But when you use it for other Indian languages, you're going to see that there are a lot of problems. And why is that the case? So it brings two kind of problems. First, it's not really pre-trained on Indian language. And the second thing is that the number of, and even for those models that have India language or say Hindi, Marathi, or have tokens associated with these languages, the problem is that the number of generation steps that you require are much larger than English. That means if, say for example, if you were to generate this much text in English, models like Llama, Mistral and others would need like 20 and 18 generation steps. But then if you generate something like Hindi, you are basically doing 4 times to 5 times more generation steps. What does more generation steps results to? It results to more computation, hence resulting in much higher cost. That means you're paying more for generating the same amount of text in Hindi compared to English. That means you're paying more to OpenAI or any other provider, or probably even you're doing more GPU cycles. And why is that the case? Let's take Llama for example, because it's open source. I will not like to comment on ChatGPT and GPT-4. But if you look at Llama, you'll see that in Llama for Hindi, you only have character-based tokens for Indian language, for Hindi, right? That means it will generate, say for example, if I want to generate Megh, which is, so there's Megh, right? So like 3 tokens. So it will need 3 tokens to generate it. Now, if you have a model that was natively trained on Indian languages, probably it can just do it in 1 token. That means you have saved like 3x, 2x of less generation steps, right? And hence, people are trying to do a lot of different tricks. Either you train it from scratch, that's a lot more expensive, but again, the advantage that you get is that you're going to have a unique proposition of building model from scratch. The second jugaad way that people are actually doing today is that, hey, I take a Llama model which is trained on English, expand the vocabulary. That means I expand the vocabulary of the Llama model on the tokenizer and then continue doing pre-training. This way, I will need obviously a lot less compute and I'll still be able to build a model that can generate these kind of subword tokens rather than character-based tokens, and hence helping me reduce the cost. Again, this is a jugaad. Obviously, people are doing it. Works decent, but does it work as well as English? Probably not. Okay, so this is how just a way to think about how Indian language tokens are getting generated. Now, again, the next most pressing question: Megh, GPUs are very costly. Deploying an LLM takes a lot of cost. How do I reduce it, right? And that's where what I really want to bring to the table is that a lot of people actually forget doing any kind of optimization. They simply take like a Hugging Face model, deploy it, and they say that, hey, it's very costly. GPUs are very costly. But in principle, it's not. Otherwise, why would people be buying GPUs if they were actually costly for deploying LLMs, right? Otherwise, we wouldn't have sold those many GPUs, right? So the reason we are selling is because if you actually do the right kind of optimization, you can actually get a lot of cost savings. And that's what our software ecosystem helps you with. Because you see, deploying these things, we also want to make sure that you make a lot of money on your application, right? We don't want all the money from it because then we don't really win. The way we win is that we make sure that you are saving a lot of cost, and that's what we put a lot of emphasis on through our software ecosystem. So if you actually see, just by moving in from a new generation of GPU plus using the right software, you can actually get 5 to 3x better or 2.5x better performance compared to natively using it, by using the same tools on a previous generation GPU architecture. So if you use the H100s, you will see that you'll get like 2.5 to 4x gains compared to an A100 GPU using the same software. And the second thing is the price of H100s are not actually it's not 3x the cost of the GPU. It's probably 1.5x that of A100 if you buy it from the right place. That's also another tricky question that, hey, anyways. Okay, another thing. It's not about just doing the software optimization in a month. Okay, we keep updating our software libraries every month. So if you see, in January, we came up with a new software update that took the same software stack, but just with more optimized kernels, you are actually able to get much better throughput, like about 2x to 2.4x for the Llama 70B model. So again, the point that I'm sort of trying to keep emphasizing again and again is the fact that please use these softwares and the latest version of these softwares to actually reduce your overall cost of serving these LLMs. Now, if you use something like Hugging Face, like a simple PyTorch interface, and then compare it with TensorRT-LLM, which is our optimization compiler for LLMs, you'll see that there's a lot of performance that you're leaving on the table. If you deploy it with PyTorch, you will get say about 1x, and then when you use TRT-LLM, you can get 5x for GPT-6B model, And if you do 70B, it's about 9x. A lot of cost savings. Obviously, we'll do more detailed things around it, but I want to show some charts so that you're motivated enough to try it in the first place. Now comes the second.
Is one part, but do you have any graph that also indicate the error, what error introducing after quantizing or going to this stage?
Again, very good question. I don't have a graph right away, but I can give some insights based on my learnings. So obviously, as you all know, these models are typically trained with BF16 or /FP16, which is like a mix, which is like single precision. Now, what we have actually seen is people are doing quantization all the way till int4. Okay, that means quantizing all the way till integer from float. Now, if you see, there are some performance improvement. That means you can go from 1x all the way to 1.6x, all the way till int4, and you can see that that's the throughput improvement, and the memory is almost reduced by 70%. Now, a second point to also bring in is the accuracy. How much accuracy am I going to lose while doing quantization? So if you see, my learning has been, when you go from FP16 to, we have this introduced a new data type called as FP8, which is floating point 8 precision in our Hopper and Lovelace, Ada Lovelace architecture. Those precisions don't affect your accuracies at all. When you go to int4 and int8, you are going to see degradation in some accuracy. Okay. In this case, it will be your benchmarks that you have for typical LLM models like MMLU, Hella, Swag, and there are multiple of them. You will see degradation when you go all the way to int4 and even integer 8. But if you are doing FP8, you are not going to see that degradation, and you are still going to see at least 1.5x improvement in performance. Okay. Again, I don't have charts for that right away, but I can share more details offline. But again, that's a very good question that, hey, how much accuracy am I going to lose? Okay, now let's go to the main software that's actually doing this. Okay, so this is called as TensorRT-LLM. Prior to this, we had this compiler called as TensorRT, and we have just added an LLM attribute on top of it because we are doing some more specialized optimization for LLMs. So you see that TensorRT-LLM is nothing but it's a graph compiler that we have built, which essentially takes this large graph of neural networks, which is basically nothing but a computational graph of tensors and operations. In this case, attention, fully connected layers, activation functions, and so on and so forth. So there's a lot of optimization that you can do on this graph. That means you can actually fuse multiple operators together. So say for example, if you're doing attention, you can basically fuse multiple operations within attention rather than individually calling these functions. So think about it like this, that you were using, say, a fully connected layer, then you were using some activation, then you were using some batch normalization. When you run this natively without any kind of graph optimization, you're gonna call 3 kernels. Kernels are nothing but computational code that runs on top of the GPUs directly. So you're doing 3 operations and 3 kernels are being called. When you use TensorRT, it fuses these kernels together as a single kernel. And when you're doing a single kernel call, you're you're basically doing less function calls, plus you're also making sure that the movement of the data is not a lot, because then within a single function call, you're doing all the 3 operations. So basically what happens is that entire graph, which had probably thousands of operations, you have reduced it from 1000 say to around 300 just by doing these kind of graph optimization. So this is one kind of optimization that TensorRT does. There are a lot more. Maybe let me talk about another one which is pretty interesting, which is in-flight batching. What does in-flight batching mean? So typically the way you think about any kind of deep neural network inferences, you take a batch of data, you feed it to the model, and then you wait for the entire output to be generated for the entire batch. Now in case of LLMs, you will see that you have a parameter called as input sequence length and output sequence length. That means for every query, your input sequence length and your output sequence length can be variable. That means you don't really need to wait for all the requests to be executed. You can basically do a smart way of batching where as soon as a request is ended, rather than waiting for all the 4 samples within that batch to be executed and then get the request 5. So here you see that request 1, 2, 3, 4. And this is the number of generation steps that have been executed. If you see that the request 2 just got completed with a single generation step, but probably R4 needed 7 generation steps, and after which it got the end of sentence token. Now you see this block, there's nothing happening. There's a bubble. You're not really using the GPUs there. Okay. So how do I make sure that these kind of bubbles, excuse me, these kind of bubbles which are there where there's no computational happening, how can I still, add more requests here? That is what continuous batching does. It basically takes the next request as soon as there's an end of a specific request, once it's done generating whatever the query was.
So this batching is handled by TensorRT-LLM, or we have to
No, you don't
batch
have to do
the
that.
queries and give
No,
it?
you don't have to do that. TensorRT-LLM has this in-flight batching mechanism included.
Because when I tested giving multiple queries, it didn't work.
Okay, maybe we can take
Yeah.
that later. But in-flight batching will be part of the TensorRT-LLM graph. Okay, and you don't need to manually do this. Okay, so this is one way, right? The second one is multi-GPU and multi-node. Now again, for small language models, deployed on a single GPU, no problem. But there are a lot of people who have realized that, hey, maybe small models are not how I'm going to generate value. So there are a lot of people who are actually deploying very large models, all the way from 100 billion all the way to about 500 billion parameters. And I'm not even kidding. This is actually a reality. And that is where the support for multi-GPU and multi-node becomes very critical, because these models don't fit on a single GPU. And quantizing doesn't make sense because, now again, this might sound a little counterintuitive. Sometimes there are cases where using more GPUs for deploying that model turns out to be more cost effective than just deploying on a single GPU. People always feel that, hey, if I can cram my model in a single GPU, I'm going to get the best cost or bang for my buck. The answer to that is no. That is not really true, right? If that would have been true, then again, we would not be selling those many GPUs.
What about the communication cost between the GPUs?
Exactly, and that is where we have this technology for doing very fast communication called as NV-Link, NV-Switch. That basically connects these GPUs over very high speed bandwidth of almost 900 gigabytes per second. And that is what the beauty is, right? So it's not about the GPU that we are building. It's actually we build the whole stack, right? From the GPUs to the interconnects that connects these GPUs within the system and also outside the system. And that is why we have so much value in the market, because we are building the end-to-end, I would say a large-scale supercomputer that can do this effectively and not a single GPU. Because even if you make a GPU very fast and if you don't have fast interconnects, you are going to reach bottlenecks. Because,
And these models typically you see being deployed as a REST APIs or what?
Yes, they are. I am coming to that. I have a very good code base and depiction of that. And then obviously you have the different kind of quantization that are supported in TensorRT-LLM. That means, hey, if you decide that, hey, I don't want to use a lot of GPUs, I want to cram everything in a single one, go ahead and use all these different kind of quantization techniques that are available in open source, which are included within TensorRT-LLM. Okay, now let's go to the server part. That means, what is a server?
Okay, is there a comparison between TensorRT-LLM and VLLM?
Actually, I have, but the thing is, we believe in partnering with a lot of people. We work with the VLLM team as well. So if you want some numbers, I can share offline, and I would want you to go back and do these benchmarking rather than I telling that, hey, we are better than somebody else, which is not what we do as a company. Right? We believe that all our partners who build on our hardware infrastructure, all of them are doing great work. It is up to you to go ahead and do these benchmarkings, but yes, you might see some goodness with our toolings. Let's go back to the server architecture. So if you look at this, the server architecture is basically responsible to take a runtime, which is TensorRT-LLM in this case. Other runtimes can be PyTorch runtime, can be TensorFlow runtime, can be Onyx runtime. So these are the runtimes, and then you have a server architecture that is responsible for getting those input requests coming in from, say, gRPC or HTTP protocol, either in terms of streams or in batch, and it's responsible for then doing something called as, basically putting in the queue, and then the TensorRT-LLM will do batching and then do the execution. And the server will return two things. One is the metrics, which is the utilization of the GPUs and the overall input-output queries, as well as it's gonna give the corresponding output of that query. So this is basically a server architecture that we have. So client submits a request, the request enters a queue, then the queue basically goes to the backend, which is the runtime, inference happens, you get a response, and it's sent back to the user. And then the metrics are emitted as well. Now let's look at a TensorRT-LLM architecture in a little more zoomed in version. Okay, so here are the requests that are coming in. You might have like an OpenAI like API endpoint, API REST signature if you want to create this. Again, this is optional. But people typically prefer this because they might be using OpenAI and they want to make sure that their REST call for their on-prem LLM model also follows the same protocol. Otherwise, what will happen is you will have two different protocols in your server architecture. So you can keep like a common OpenAI like API endpoint protocol, not protocol, but these REST signature of your server. And then basically you have two things. You have the TensorRT-LLM engine, and then you have a model ensemble. Now what is this ensemble? So like I was telling you previously, you have a pre-processing stage, you have a LLM model stage, and then you have a post-processing stage. You basically combine all of these as one computational graph through Triton. So Triton can basically take a tokenizer, which is the pre-processor, TensorRT-LLM runtime as the model instance, or as the execution runtime, and then the post-processor again is a Python process that takes the tokenizer and does de-tokenization. And you combine all of these as an ensemble graph through Triton. And then you basically run this. So now let me show you the code. I know I've almost crossed the time, but I'm just going to take one more quick minute to just show that. And if there are any more questions, maybe we can do a post-session follow-up on that. Just give me 1 second. I'll just quickly run through the code. It's quite short and simple. Okay. So let's look at the entire thing that I told you, right? It's not like 1,000 lines of code. So this is my GPU instance. I have like two A100 GPUs. Now, if you see, I'm going to take the Llama model. The Llama model is sitting in this directory. The precision in which I'm going to deploy this is float 16. And I'm going to say that my maximum input batch size will be 16. My maximum input length will be 1000, output length will be 1000. And I want to basically use some specialized gem plugins and GPT attention plugins. And plugins are basically those fuse, telling the TensorRT-LLM that, hey, you need to fuse these kernels in very simple terms. And then you have like a very simple build.py file, which is available in open source. You basically execute this build.py file, which will start building the TensorRT engine. And once this engine is created, you can basically see it looks like this. Models, oh no, sorry, it's not here. It's a workspace. Engines, Llama 16B. Yeah, you can see that there is basically these three files, model cache. This is the engine, which is the TensorRT-LLM optimized graph of that model. And then you have a config.json file. So this is the output that you get after you run the TensorRT process. Once this is done, I'm just going to show you that I'm going to run a simple inference on top of it. So this is the build phase. Now I'm just using a run.py file that will take that engine and will start. Okay, this looks weird.
Can we run multiple instances of run.py?
You can do that, yes. I think there was oh, okay, I got it. What happened? I just need to provide the path. I think this variable was not set. Maybe let me just run the cells on the top. Cool, I think it has started. Okay, just ignore this for now.
It used to crash as soon as we get multiple GPU occupy for manually check करना पड़ेगा, but I'm sure it is going to be so get you lock here one by one. That's how we do it. I don't know if there is a better solution. That's how I was looking for. This is a hack actually. What is a better solution to handle?
Okay, I think that was
the it is crossing.
Yeah, I think it has started to generate now. If I just do NVIDIA SMI, yeah, you can see that there's some computation that's happening. 85% of SM utilization, 245 watts of power being consumed out of 400, and 14 GB of GPU being used. So yeah, the generation is complete. We have completed it, and you can see that the output is now generated using the TensorRT-LLM engine file. Then you basically do Triton, which is the server which will be running on top of this. And like I said, you have a pre-processor, you have the model which is TensorRT-LLM based, and then you have the post-processor, and then you have an async Triton client. Now I'm simply going to show you the tree structure of this, right? So you can see that it's pretty simple. There is a simple folder called as model repo llama. You have this ensemble that is connecting the pre-processor, TensorRT-LLM, and the post-processor together. So this is the structure of the deployment directory. Again, very simple, nothing complicated. and then I can basically use this command to start that server. So let me just run it. As you can see now, the Triton server is starting. It's going to load all the modules, which is the preprocessor, post-processor, TensorRT-LLM, and the ensemble that will connect all of these. So it'll take few seconds to get this loaded, and once this is loaded, then we'll hit the server using a curl command and a simple Python script. Yeah, so the server is running. So the gRPC service is running on 8001, HTTP service is running on 8000, and the metrics is on 8002. So I've deployed the server. Now I can do a simple curl command like we do for OpenAI. Give some input variables. Given this is my input text. This is the max tokens. I have not passed any bad words or stop words, and you can see that it has generated this particular text using that curl command. And then obviously you can do that using a simple run.py utility as well. So yeah, in interest of time, I think that's what I had. If there are any questions, feel free to. Yeah.
Is there any reason why you don't support TensorRT-LLM service support any specific models? We have tried a few and some of them are not.
Any example of that? No, it does. We do support Mistra. So I'll just show you. So it gets updated every month. Now the thing is, which version you're using becomes very important. I'll just show you all the models that are supported, right? If I just go on, say, support models, yeah. So you can see this is the list of supported models, and you can just look at, we do support Mistral, and also Mixtral, which is the mixture of expert. Even that has been added this month. Sorry. Oh yeah, the Mixtral, yeah, the one with the X, which is a mixture of expert model, which is 8x7b. That is also supported. This is the main branch. This would be 0.9, but I think 0.8 will also work with Mistral. Yeah.
We are doing any good for LLM inference on Edge.
On
Edge.
Oh, Edge. Oh yeah, absolutely. So we have this product called as Jetson. Now on top of Jetson, you can run any CUDA program. That means you can obviously run TensorRT-LLM as well.
So you have mentioned about developing LLM from scratch in English languages. Will it have same reasoning or intelligence as those are developed in English language? Because what we see in market from Ola, it's giving not good answers. As if we ask questions in Hindi to OpenAI, GPT is giving better answers in Hindi.
See, I mean, again, it's a little controversial question, so I'll try to be a little more specific. If you do it right, it'll work.
Stay away from it.
Yeah, but I'll actually add on the Krithrim part. See, I mean, none of us here really got a chance to use ChatGPT, on the 7th day when it was launched, right? I know the people who got on it, on day 2, day 7, day 15. It was really, if you would have seen it, you would have said, no, this is useless, right? That's where Krithrim is right now. Even with everything, it is going to take some time, definitely.
And see, again, the way I also would want to also put out is, see, it takes time. It takes time for people to take the feedback that is coming in, reiterate and make it better. So it's not like, anybody has done a bad job. I think that is part of the process. That is how people build LLM models. Like, you build it, you deploy it, you take feedback, based on that feedback, you improve your data, do the alignment in the right way, and then redeploy. Again, take more feedback, improve it. It's a continuous cycle. People think that, hey, LLM le lo, deploy kar do, ho gaya, mera life sorted. That is not how it works. It's a continuous cycle. You have to keep improving it again and again. You will run into a lot of issues and failures, but that is part of the process. And I think we should just appreciate the effort that people are at least putting in to even build this out, right? So I just think that, whatever Krithrim is building is great. We just need to support them rather than always being like, hey, it's not working. I think that's not the right thing to do.
Yeah, I think we can take other questions.
Yeah, we should take it later,
yeah. Yeah, okay. So thank you so much, Megh. Round of applause for you. Up next, I would like to call